Hello friends, in this video we are going to have a discussion on gaseous state. Well, any matter or any compound will behave like a gas if thermal energy between their molecules is greater than that of force of attraction between them. So if any compound is behaving like a gas, then the thermal energy between its molecules is always greater than that of the force of attraction between them. So while studying this behavior of gases, several laws were developed. The first one is Boyle's law. Boyle's law. This law states that at constant temperature and amount of gas, that is number of moles. So if the amount of gas and temperature is constant, then pressure is inversely proportional to the volume of the gas. So we can also write it as the product of P into V is always constant. So in case of ideal gas, if temperature and the amount of gas is constant, then the product of pressure into volume is always constant. So if we plot pressure versus volume at two different temperatures, then we will get a plot like this. This is T1, this is T2. So T2 is greater than T1. So this temperature is greater than that of this temperature. Another law is Charles' law. Charles' law. Charles' law states that if pressure and number of moles are constant, so if pressure and number of moles are constant, then volume of a gas is directly proportional to the temperature of the gas. Therefore, V upon T is constant. Okay. So if we plot volume versus temperature, this is volume, this is temperature, then we will get a plot like this. If they are plotted at two different pressures, this is pressure P1, this is pressure P2, where P2 is greater than P1. So there is another law known as Gaseous law. This is Gaseous law. This law states that pressure is directly proportional to temperature, volume and amount of gases are constant. Or P upon T is constant. Okay, so one more law was developed known as Avogadro's law. Avogadro's law. This law states that if pressure and temperature are constant, then amount of gas is directly proportional to the volume occupied by that particular gas. Okay, so all of these laws were combined together. Combining these laws, it was observed that P into V upon N into T, it always comes out to be a constant quantity. And hence, scientists arrived at a formula which looks somewhat like this: P into V equals N into R into T. This is known as ideal gas law. Ideal gas law. Okay. So where R is universal gas constant, universal gas constant, and its value is 8.314 joule per Kelvin per mole, or 0.0821 atm liter per Kelvin per mole. So the value of R depends on the units that we are employing. It is also equal to 2 Kelvin per mole. So with units, the value of R keeps on changing. So now let's discuss about Dalton's law of partial pressure. Dalton's law of partial pressure. It states that, as we have already discussed in our discussion on mole concept, that Dalton's law of partial pressure states that P total equals summation of the pressure exerted by individual gases present in that mixture, and the mixture should be non-reactive. And by applying that ideal gas law, we can say that P total equals N total into RT upon V. Since R is constant, T is constant, and V is constant, we can say that P total upon Pi, that is pressure exerted by ith gas, equals N total upon Ni. So from here we get that Pi equals Xi into P total, where Xi is the mole fraction. Xi is mole fraction. Okay, so another law is known as Amagat's law of partial volume. Similarly, like Dalton's law of partial pressure, Amagat's law states that volume occupied by ith gas equals mole fraction of ith gas into volume total. That is total volume occupied by the mixture. V total is the total volume occupied by the mixture. So V total into Xi gives Vi. Now let's discuss about diffusion first. So in case of diffusion, now diffusion, it is a mixing of two or more gases due to partial pressure difference. A gas would move from its region of high partial pressure to the region of low partial pressure, even if it is against gravity also. So at the end, the gases would have the same partial pressure everywhere. So the only aim for diffusion is to occupy the space such that they have same partial pressure everywhere. So in case of diffusion, another one law came. Graham, we call it as Graham's law. Graham's law. Okay. According to this, rate of diffusion or effusion, rates of diffusion or effusion R is inversely proportional to 1 upon under root m, where m is the molecular weight of that particular gas. So there is an equation for rate of diffusion. For rate, R equals P into A upon under root 2 pi R into T into M, where P is the pressure, A is the area of the orifice, divided by under root 2 pi R is the universal rate constant, universal gas constant, T is temperature, and M is the molecular weight of that particular gas. So from here, you can say that R is inversely proportional to 1 upon root M, inversely proportional to 1 upon under root of temperature, it is directly proportional to pressure, and it is directly proportional to the area of that orifice. And hence, R1 upon R2, if we compare the rates of two particular gases, gases 1 and gas 2, we will get the expression as R1 upon R2 equals under root M2 upon M1 equals under root T2 upon T1 equals P1 upon P2 equals A1 upon A2, provided all other factors are constant. That is, if we are considering under root M2 upon M1, then pressure, area and temperature should be constant. Okay. Now, let's discuss the speeds at which gases move. We denote the speeds at which gases move by three quantities known as RMS speed, URMS. It is another term is most probable speed and average speed. Okay. So RMS speed, its expression is under root 3 V upon M, or 3 RT upon M if the number of moles is 1. So, or under root 3 nRT upon M if there are n number of moles. Most probable speed will be under root 2 RT upon M or under root 2 into nRT upon M if this is for n number of moles and this is for 1 mole. Similarly, U average is under root 8 RT upon pi M or under root 8 nRT upon pi M. So from here we get the value of average kinetic energy, that is average kinetic energy. It is equal to half M URMS square. So if we substitute the value of URMS, we get the value of average kinetic energy, half M into 3RT upon M. M to M will get cancelled. This comes out to be 3 by 2 into RT. So if there are n number of moles, then this will be 3 by 2 into nRT. Okay. Now there is one equation that came out for real gases, as we know that the ideal gas do not exist in reality. Therefore, when the Walls came out with an expression for real gases, we call it as van der Waals equation of state for real gases. E equals nRT is the equation of state for ideal gases. This is the equation of state for real gases, which is P plus A n square upon V square into V minus n B equals n into R into 2, where A and B are known as van der Waals constant and it is different for different gases. Okay, so if we compare real gases and ideal gases, then we come up with another term called as compressibility factor. Compressibility factor. It is the amount by which any gas is deviating from its real behavior. So, compressibility factor is denoted by Z and it is equal to volume occupied by that real gas and divided by volume occupied if the gas is ideal. Or this is equal to P into Vm, and since Vm equals RT upon P, so this will be P into Vm upon RT. We have just substituted Vm ideal equals RT upon P. Okay, so or if Vm we can write simply as PV, so Z factor is, that is compressibility factor is PV upon RT. Okay. So now let's get to the questions. Let's discuss some of the questions. The question says that 500 milliliter of nitrogen at a pressure of 700 millimeter of Hg and 600 milliliter of oxygen at 800 millimeter of Hg are passed into 2-liter flask at the same temperature. Calculate total pressure of mixture of gases. Okay. Now, when 500 ml of nitrogen is passed into a 2-liter of flask, it will now occupy 2 liter. Gases occupy the amount of volume that is present to them. Therefore, if whenever a particular amount of gas is passed into a restricted space, then it will occupy all of the space. And hence, when in this question, when 500 ml of nitrogen is passed into a 2-liter flask, it will now occupy 2 liter. Since the number of mole of nitrogen is same as before, and so the temperature, solution, since number of moles and temperature are constant, therefore we can say that P1 V1 equals P2 V2. That's Boyle's law is applicable here, and hence the new pressure, the new pressure of N2 would be 700 into 500 upon 2000. 500 is the initial volume, 2000 ml is the final volume, 700 millimeter Hg is the initial pressure. Okay. So from here Pn2 comes out to be 175 millimeter Hg. Okay. Now similarly final pressure by O2 is 240 millimeter Hg, as P2 now is equal to P1 V1 upon V2. Okay, and hence we can say that P total, applying Dalton's law of partial pressure, P total equals Pn2 plus P02. It is equal to 175 plus 240 millimeter Hg, or this applies that P total equals 415 millimeter Hg. This is the final pressure that we were supposed to get. Now, let's discuss another problem. The problem says that two containers A and B of equal volume hold 50 gram of nitrogen and 75 gram of oxygen respectively at the same temperature. The temperature is same. We have got the first condition. Now both containers are kept separately in vacuum. Calculate the ratio of rates of effusion of N2 to that of O2 if the area of orifice of both containers are same. Area is same, two containers of equal volume. So volume, temperature and area, these three quantities are same. Okay. So we have got two containers of same volume. The one contains 3 mole of N2 and another container contains 5 mole O2. Since all the other factors are same, volume is same, temperature is same, and area of orifice is same. So first volume and temperature is same. Since volume and temperature is same, pressure is directly proportional to the number of moles of gases. So therefore, this implies PN2 upon PO2 equals 3 upon 5. Right. Now, number of moles of N2 equals 50 upon 28. Since amount of N2 is 50 gram, molecular weight of N2 is 28. And number of moles of O2 equals 75 upon 32. So from this we get that pressure of N2 upon pressure of O2 equals number of moles of N2 upon number of moles of O2 equals 50 upon 28 into 32 upon 75. Okay. So hence rate of effusion of N2 divided by rate of effusion of O2 equals pressure of N2 upon pressure of O2 into molecular weight of O2 upon molecular weight of N2. So from here we get 50 by 28 into 32 by 75 into under root 32 by 28. So from here rate of N2 upon rate of O2 equals 16 upon 21 into under root 8 upon 7, or if we simplify it, we get the value as 0.8145. So this is the ratio of rates of effusion of nitrogen with to that of rate of effusion of oxygen. Now coming to another question. The question says, suggest the pressure and temperature at which 1 mole of H2S will be in states that correspond to 1 mole of N2S, 1 atmosphere and 25 degrees Celsius. Well, this type of question can come in the examination as a part of linked paragraph type questions. Okay, so for this, to solve this question, we need to know another concept, the concept of critical parameters. Concept of critical parameters. Critical parameters. Under this, we study critical volume, which is equal to 3 into B. B is nothing but the van der Waals constant. Critical pressure, it is A upon 27 B squares, and critical temperature, which is 8 A upon 27 R B. A and B are the van der Waals constant and R is the universal gas constant. Now, pressure, critical pressure is the pressure that if above which no matter to what amount I raise the value of temperature of that particular gas, the gas will not be converted in gaseous state. It will always remain in liquid state. And the critical temperature is the temperature above which no matter how much I press that gas or how much I increase the pressure of that gas, the gas will always remain in the gaseous state. Okay. So, now in this question, we need to understand that states that have same reduced pressure, temperature and volume are said to correspond. They are said to correspond. So this was the concept that was required in this question, and some factors were given to us, some variables were given to us. The given variable was critical pressure for N2 is 33.54 atm. Critical temperature for N2 is 126.3 Kelvin. Critical pressure for H2S is 88.3 atm. And critical temperature for H2S equals 373.2 Kelvin. Okay. So you know now what is the critical pressure and temperature of N2 and S2S, and you are familiar with their concept, what it is, critical temperature and pressure by definition. Now let's go on to move to solving this problem. Reduced pressure is given by pressure by critical pressure, and reduced temperature is given by temperature upon critical temperature. So the temperature at which the gas is and the critical, divided by the critical temperature of that particular gas, we get the value of reduced temperature. Okay, so now for N2, reduced pressure is 1 atm, that is given in the question. The states correspond to 1 mole of N2 at 1 atm and 25 degrees Celsius. So temperature is 298 Kelvin. Okay, so 1 atm upon 33.54 equals 0.030. And reduced temperature, the reduced temperature for N2 is T upon Tc, and temperature is 25 degrees Celsius, that is 298 Kelvin. So 298 Kelvin dividing it by 126.3, we get its value as 2.36. Okay. Now for H2S, we need to calculate temperature and pressure for H2S. Now we know the reduced pressure and reduced temperature for H2S because it's the reduced temperature and reduced pressure will be same as that of reduced temperature and reduced pressure of N2, because both of these gases now correspond, and hence we know that pressure equals reduced pressure into critical pressure. Reduced pressure is 0.030, and critical pressure is given to us as 88.3 atm. And hence, into 88.3 atm, we get the value of pressure for H2S as 2.6 atm. Similarly, temperature equals Tr into Tc. Reduced temperature is 2.36. Critical temperature is 373.2 Kelvin equals 881 Kelvin. And now we can say that at a pressure of 2.6 atm, we have got the pressure as 2.6 atm, we get the pressure, and the temperature as 881 Kelvin. Hence we can say that at a pressure of 2.6 atm and a temperature of 881 Kelvin, H2S gas corresponds to that of nitrogen, which is at 1 atm and 25 degrees Celsius. So the purpose of discussing this kind of problem is that we should be familiar of the reduced and critical parameters, because these kind of problems may be asked as a linked paragraph type questions. Okay. So moving on to next question. This is an IIT JEE question. It came in mains. When the subjective pattern used to be there for IITs in mains. So the question states that one way of writing the equation of states for real gases is PV equals RT 1 plus B upon V plus something going on, where B is a constant. Now derive an approximate expression for B in terms of van der Waals constant A and B. Okay. So we know that van der Waals equation, we know that for one mole, van der Waals equation is P plus A upon V square into V minus B equals RT. So from here we get P plus A upon V square equals, V bar equals RT upon V minus B. So this is the equation for van der Waals equation while rearranged. Okay, so we can write that equation as E equals RT upon V bar minus B minus A upon V bar square. This gives us P V bar equals RT V bar upon V minus B minus A upon V bar. We have done nothing, we have just multiplied both sides by V bar. Okay. So, writing this expression, rearranging this expression, we get P V bar equals RT V bar upon V bar minus B minus A upon V bar RT. Okay. So, from here we get E V bar equals RT 1 minus B upon V minus 1 V bar minus A upon V bar RT. Okay. Now, at low pressure, V bar is large, and therefore V upon V bar is very, very smaller than 1, because B is already small, V bar has become large, and hence V upon V bar is very, very smaller than 1. Therefore, the term 1 minus B upon V bar minus 1 can be expanded. It can be expanded into a power series. Okay, so let's do it. Since 1 minus V upon V bar minus 1, it can be expanded into a power series in V upon V bar. So if we do it, we get the expression like 1 minus V upon V bar to the power minus 1 equals 1 plus V upon V bar plus V upon V bar whole square. Okay. So from here, therefore, PV bar equals RT 1 plus B upon V bar plus B upon V bar square going on minus A upon V bar RT. Okay. Now, rearranging this expression, we get something like E V bar equals RT 1 plus 1 upon V bar B minus A upon RT, and these expressions are going on here. So from here, now we have got the value of PV bar equals RT 1 plus 1 upon V bar B minus A upon RT plus, and now if we compare that expression that we have got with the expression that is given in question, we get the value of B as, so from here the value of B comes out to be B minus A upon RT. This was the answer. A and B are the van der Waals coefficients for of that particular gas, and B equals B minus A upon RT. The parameters like B are known as bireal coefficients. So this we will be studying at a higher level. This is out of this scope, and this type of equation is known as equation of state for real gases in terms of bireal coefficients. Okay, so now let's move on to another question. The question says that 20% of surface sites have adsorbed N2. On heating, 20% gas evolved from sites and were collected at 0.001 atmospheres and 298 Kelvin in a container of volume 2.46 centimeter cubed. Density of surface sites is 6.023 into 10 raised to the power 14 per centimeter square and surface area is 1000 centimeter square. Find out the number of surface sites occupied per molecule of N2. Now we have to find out in this question that how many sites are occupied by one molecule of N2. Okay. Now since the values that are given is P pressure of N2 equals 0.001 atm, temperature equals 298 Kelvin and volume is 2.46 centimeter square. Now by ideal gas law, PV equals nRT. So from here the value of N equals PV upon RT. So value of N of N2 is 0.001 into 2.46 into 10 raised to the power minus 3. We are converted the volume into liters, okay, or meter cube. 0.081, this is the universal gas constant into 298 value. So from here N2 is number of moles of nitrogen is 10 raised to the power minus 7. So therefore number of molecules of nitrogen equals 6.023 into 10 raised to the power 23 into 10 raised to the power minus 7. So from here it comes out to be 6.023 into 10 raised to the power 16 are the number of molecules of nitrogen gas. Okay. Now since total surface sites available, equals 6.023 into 10 raised to the power 14, because here is the density of surface site and here is the area, total area, and hence we can say that total number of surface sites available equals 6.023 into 10 raised to the power 14, that is density into area. It comes out to be 6.023 into 10 raised to the power 17. Okay. Now therefore surface site used to absorb N2 equals 20 upon 100 into 6.023 into 10 raised to the power 17 equals 12.04 into 10 raised to the power 16, because it is given in the question that 20% of surface sites have been absorbed by N2, and hence since total number of surface sites is this, the amount of surface sites absorbed by N2 is 20% of that particular value. It comes out to be 12.04 into 10 raised to the power 16. Okay, so hence the number of sites occupied by one molecule of N2 equals total number of sites absorbed by total number of atoms. It comes out to be equals to 12.04 into 10 raised to the power 16 divided by 6.02 into 10 raised to the power 16. So this value comes out to be equal to 2. So hence two sites are absorbed by one molecule of nitrogen by one molecule of nitrogen, and So this is the question. Now this question appeared in IIT JEE. This question appeared in IIT JEE 2005. Now let's discuss one more question. The question says that a container holds 3 liters of nitrogen and H2O at 29 degrees Celsius. The pressure is found to be 1 atm. The water in the container is instantaneously split into hydrogen and oxygen by electrolysis according to the reaction H2O giving us H2 plus half O2. After the reaction is complete, the pressure is 1.86 atm. What mass of H2O was present in the container? The aqueous tension of H2O at 29 degrees Celsius is 0.04 atm. That is, the pressure exerted by H2O at 29 degrees Celsius is 0.04 atmospheres. Now, let's get on to solve this question. So, according to the given conditions, total pressure in the beginning equals pressure exerted by N2 plus pressure exerted by H2O. Because applying Dalton's law of partial pressure, this is the total pressure. So the total pressure is 1 atm and hence pressure N2 equals 1 minus 0.04. Since the aqueous tension of H2O is 0.04 atm and hence pressure exerted by H2O is 0.04 atm and total pressure is 1 atm. And hence pressure exerted by N2 is 0.96 atm. Okay. Now when water is split into H2 and O2, the total pressure is, when water is split, total pressure, P dash D equals 1.86 atm. Okay. And therefore pressure by N2 plus pressure by O2 plus pressure by H2 when after the splitting of water is 1.86. Okay. Now pressure exerted by N2 is 0.96. So therefore 0.96 plus 3 by 2 pressure of H2, 0.96 by 3 by 2 pressure of H2 equals 1.86. This is because pressure exerted by H2 equals twice of pressure exerted by O2. Because here after the electrolysis, 1 mole of H2O gives 1 mole of H2 and half mole of O2, and hence the pressure exerted by H2 will be double because number of moles of H2 is double than that of O2. Now, therefore, pressure exerted by H2 equals 1.86 minus 0.96 into 2 by 3 gives us 0.6 atmospheres. Okay, and as number of moles of H2O equals number of moles of H2, because 1 mole of H2O gives us 1 mole of H2, hence number of moles of H2 equals PV upon RT. This equals 0.6 into 3 upon 0.0821 into 302. So from here number of moles of H2 equals 0.0726 mole. Okay, now therefore mass of H2O equals 0.0726 into 18 equals 1.306 grams. Okay, so this is what we were supposed to calculate, that the mass of H2O that was present in the container. Now, this method looks absolutely perfect. It is very fine, but there is an error. It is so small that it is very much difficult to point out. Okay, so there is a trick in this question. Now just try to find out what the error can be, and just pause the video and try to find out what the error can be. Okay. Now if we look at it closely, if we look at the solutions very much closely, it looks perfect, but there is an error, and the error is that the pressure of one atmosphere is no doubt the pressure of N2 and H2O vapors, but the electrolysis is done only to H2O. In question it is given that the water, the H2O in the container is instantaneously split into hydrogen and oxygen, and hence the pressure of 1 atm is the pressure by N2 and H2O vapors, but electrolysis is done only to H2O, and that too instantaneously. This implies that H2O that is in vapor form, that was in equilibrium with the liquid initially, would be still left after the complete electrolysis of liquid water. And therefore 1.86 atmosphere is the pressure of H2O2 N2 along with H2O, since this will still be left in the system, and hence since we have taken here 1.86 to be equal to PN2 plus PO2 plus PH2, here it will also be equal to plus PH2O, and therefore there is an error. Now the correct solution will be PN2 plus PH2 plus PO2 plus PH2O equals 1.86. Okay, now combining these two, we get, and writing the value of PN2, we know the aqueous tension of PH2O, that aqueous tension of H2O, so we know the PH2O. Therefore 3 by 2 PH2 plus 0.96 plus 0.04 equals 1.86. So from here we get the value of PH2 as 2.3 into 0.86 equals 0.5734 atm. And since we know the pressure exerted by H2 now, hence NH2 will be 0.5734 into 3 upon 0.082 into 302. It comes out to be 0.694. Okay. And now since the number of moles of H2 equals the number of moles of H2O, therefore number of moles of H2O equals 0.694 moles. And therefore mass of H2O equals 0.694 into molecular weight of H2O, which is 18, equals 1.25 gram. It's almost equal to 1.25 gram. So initially it may look like that this is the correct solution, but it is not, because the only thing that you should keep in mind that after electrolysis water will be left in the container. Okay. So let's discuss one more question, the last question of the video. The question says a 5 liter flask containing nitrogen at 1 atm and 25 degrees Celsius is connected to a 4 liter flask containing nitrogen at 2 atm and 0 degrees Celsius. After the gases are allowed to mix, keeping both flasks at their original temperatures, what will be the final pressure and the amount of nitrogen in the 5 liter flask? Assume ideal gas behavior. So now we need to find out the final pressure and the amount of nitrogen in 5 liter flask. Okay, now so let's try to solve this question. The total amount of nitrogen in the combined system is total amount of nitrogen and T equals N hot, that is the number of nitrogen present at cooler temperature plus the number of nitrogen present at a hot temperature plus the number of present at lower temperature. So total number of moles of nitrogen is moles of present in hot conditions plus number of moles that are present in cold condition, and therefore N total equals P hot plus, it's P hot into V hot upon R into T hot plus P cold into V cold upon R into T cold. Now hot, the higher temperature, the system which is at higher temperature has got the temperature equals 298 Kelvin, and the system which is at lower temperature has got the temperature as 273 Kelvin. Therefore, N total will be 1 into 5 upon 0.08 to 1 into 298 plus 2 into 4 upon 0.08 to 1 into 273, which gives us N total equals 0.204 plus 0.357, which is equal to 0.561. Now after mixing, P hot equals P cold, the pressure will be same in both of the cases, and therefore N hot into R into T hot upon volume hot equals N cold into R into T cold upon V cold. Now since the amount of gases will be changed, therefore this will not be that of initial value that we have got, and hence let's denote it by N dash, the final number of moles. Now let the number of moles of N2 left in the container at 25 degrees Celsius be X. Okay, so let the number of moles left in the container at 25 degrees Celsius equals X. Then the number of moles of N2 at 0 degrees Celsius would be, therefore number of moles of N2 at 0 degrees Celsius would be 0.561 minus X, because the total number of moles will be same in both of these conditions, and therefore X into 298 upon 5 equals 0.561 minus X into 273 upon 4. So simplifying this, we get the value of X as 0.299, and therefore moles of N2 in 5 liter container equals 0.299, and therefore the final pressure of 25 degrees Celsius container is 0.299 into 0.08 to 1 into 298 divided by 5, and hence from here we get the value of pressure as 1.465 atm, and hence the final pressure and the amount of N2 in 5 liter flask is 1.465 atm and 0.299 moles respectively. So these are the values that we are supposed to get. So this problem is solved, and that's all with this video. See you in the next video.